All right, in video 2, we're going to start off by, we're going to look at basically the same function that we just kind of finished with. So what you can see here, f of x is defined to be x minus 2 over x squared minus 4. That's the same function that we had on the previous page, as long as x does not equal 2. So that's our condition. As long as x doesn't equal 2, it's the same function that we had. But then the piecewise part of it says, well, we're going to let f of x equal 3 when x equals 2. So basically that means that when x equals 2, the y value is 3. So we're redefining the function. So I'm not going to redraw the entire function. I'm going to go back to the previous page here, and I'm going to just add that extra piece in here, partially because I'm lazy and I just don't want to redraw the entire thing. If I say that now when x equals 2, the y value is 3. Well, 3 might be maybe someplace up in here somewhere. So when x is 2, now y is 3. Basically, that just gives me a point right there. Okay, so that's what we're looking at now. So we have a function which has been redefined piecewise, and it's still a function because it passes the vertical line test because that solid dot is right over top of the hole. So we're okay. So now if we want to say, now let's find the limit as x approaches 2 of this function. So the graph is now defined. It has an actual value at x equals 2. And the limit of that function, well, let's look at the graph again. The limit of this function as x approaches 2 doesn't change. It's still approaching 0.25. The fact that we changed the value or added a value of 3 there makes no difference to the limit. Remember, the limit is not what the y value of the function is. It's what does the y value approach. Well, what the y value is approaching is still 0.25 if you look at that graph. Even though the value jumps way up to 3, the y values are approaching 0.25 as they get really close to x equals 2. It's not necessarily going to be the value of the function at x equals 2. So going back here, the graph is now defined at x equals 2, which was y equals 3, but the limit is the same as it was before. That doesn't change. That's a very important concept. So let's go ahead and do something down here with these 3 graphs that hopefully will illustrate what I'm talking about. I'm going to try to do my best here of drawing the same graph 3 times, even though I probably won't be able to do it very well. Draw one like this, and then I'll try and do the same thing again, and then I'll try and do the same thing again. Those aren't bad, but they're not perfect. I know there's a way to like copy and clone, but I'm not worried about doing all that. So the only thing that I'm going to do here is I'm going to change the second graph and the third graph. So I'm going to do a little bit of erasing here. Right here I'm going to erase, and right here I'm going to erase about that same place. And I'm going to exaggerate a hole right there, and I'm going to exaggerate a hole right there. And then the last one, I'm actually going to define a point right there. So let me go ahead and finish connecting these the way they should be connected. All right, so basically this is the same graph. So we're going to call this point right here, that value, that x value A. Same place here, we'll call that A. And then if I can do it about the same place here, we'll call that A. So the idea is this. If I want to find the limit of the first graph as x approaches A, well, I can simply go up here and say, okay, what is that y value approaching? Well, since it's completely continuous, there's no holes or anything, it's whatever that y value actually is on the graph. The y values are approaching whatever that is, and we're just going to call that limit L. Well, because there's a hole there, it doesn't really change anything. I'm still asking myself, what does the y value approach as I approach that hole, as I approach x as A? Well, it happens to be exactly the same L value. Again, this is assuming that I can draw this correctly. And then in the last one, which is very much like the example that we just did, as x approaches A, it's approaching that hole. It's not approaching the red dot, it's approaching that hole on both sides. So the limit as x approaches A still happens to be L. They're all exactly the same. So it doesn't matter if you have a hole, it doesn't matter if you have a value outside of that hole that's different, or it doesn't matter if it's continuous. As x approaches a, the limit is still going to be exactly the same y value. So what can we say there? We can say that the only thing that matters is how f of x behaves near a, not the actual value of f of a. So it's not the function evaluated at a necessarily, it's how f of x behaves near a. Okay, that's what we're looking at there. Very, very important concept. All right, let's go on to the next page. All right, so if we were going to look at this function, we want to take the limit of as x approaches 0 of sine of x over x. So it says guess it. So if you want to put that in your calculator, you can. Just make sure that when you put these things with trig in your calculator, you're in radians, because otherwise it won't graph correctly. But we could also just plug it in and look at a table of values to figure it out. If you kind of plug it in and you zoom in a little bit on what this graph looks like, in your calculator, it might look something like this. If you zoom in enough. The problem is your calculator cannot actually show what's actually happening as x approaches 0. Now you might look at that and say, oh, I can pretty much tell by looking at my calculator what this thing looks like it's approaching. But if you were to directly substitute 0 into sine of x and 0 into the denominator, well, first of all, you know that 0 in the denominator is a problem. But sine of x or sine of 0, we should remember with our trig values is also 0. So that would really give you a 0 on top and a 0 on the bottom in this thing. Well, that creates a hole in the graph. So once again, your calculator can't really show this, but there's actually a hole right there. One way or the other, you should still be able to look at that and say, oh, I think I know what that's approaching. Again, if you zoom in far enough, you can kind of see the y value that's there. But what we can do is we can take x to be plus or minus 1. Doesn't really matter if it's positive 1 or negative 1. If you plug in a positive 1, you plug in a negative 1, you're going to get the same value here. And that's because hopefully you can see that on either side of your graph, positive and negative 1 is going to yield the same y value. Hopefully you can see that by the way this thing is graphed. So if I plug in positive or negative 1 into sine of x over x, I get 0.841. And then if I plug in 0.5, because that's getting closer to 0, I get 0.958. And if I plug in 0.4, I get 0.973. And if you've already guessed this, then you pretty much know that you're probably heading in the right direction here. You plug in 0.3, you get 0.985. And as we start getting closer and closer, I'm just going to start filling in these values. And hopefully that will confirm what maybe you already thought the values were approaching. Obviously 0.001 is very, very close to 0. So it looks pretty obvious that the values here are approaching 1. And so we're going to say that the limit as x approaches 0 of sine of x over x is 1, based upon our numerical analysis there. We are actually going to be able to show that and prove that later on, but for right now, we're just going to assume that that is the case because it looks like it is numerically. So remember that the existence or the non-existence of f of x at x equals c has no bearing on the value of the limit of f of x as x approaches c. So it doesn't actually have to exist. As we clearly saw on that one at the top, there's a hole there. It doesn't actually have to exist in order for this to work. We do have a limit there, and it looks like that limit is 1, and it is 1. Limits can also, however, fail to exist. Oh, by the way, star this one. That is a limit that you're going to need to know. It's just one of the special limits. There's another one that we're going to be doing, but that's one of them. I'll explain more about this one specifically in detail, but star that one. You need to know that one. Limits can also fail to exist. Okay, and this gets a little bit more interesting, at least I think it does. If you were to try and take the limit as x approaches 0 of sine of 1 over x, well, this is an interesting one in the fact of what it does. This is really, really difficult. If you graph it on your calculator, it's going to look really strange. What this thing does is it actually does something like this. It starts off a little bit wider over here, and then it starts to get much, 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 much closer to the point where you really can't even tell what's going on. Now, it's going to keep getting closer and closer to the y-axis, but it'll never get there. And likewise, it'll do exactly the same thing from the other side. It'll start doing this, and then it'll start bouncing up and down and getting closer and closer and closer to the y-axis, but it'll never get there. This is what's called an oscillating function, meaning that the function is going to bounce back and forth, up and down constantly as it approaches the y-axis, but it will never approach a specific y value. It's just going to keep bouncing back and forth, up and down. Again, very difficult to see in a calculator. You'd never really realize that's what it's doing unless you started looking at really, really small values. But what we say here is that the limit does not exist due to oscillating behavior, meaning it does not approach a single y value. It's going to keep bouncing up and down on both the left and the right side of 0 as it approaches 0. Okay, a very interesting function. That is one way that a limit can fail to exist. Okay, there are other ways, and these will be slightly more useful because we don't see the oscillating one a lot. It'll come back a couple of times, but it's not frequent. First of all, the graph of 1 over x squared, we kind of need to know what that looks like. It's very similar to 1 over x. If you remember, 1 over x, at least on the right side, looked like this. On the left side, it was in the lower left-hand quadrant, basically what would also be the third quadrant. But because it's x squared in the denominator, you're not going to get any negative values. Any number you plug in there, you're not going to get anything negative. And what it does is it actually reflects the left side above the x-axis to look like this. So it makes it kind of symmetric around the y-axis there. And then once again, you have your vertical asymptote here at 0. Because if you plug 0 in, you get 1 over 0, and that's a problem. So what you can see is the limit as x approaches infinity, well, both of those graphs seem to be going in the vertical direction. They seem to be going up. And as a matter of fact, both of those things are going to head off towards positive infinity. But this is a really big key. Infinity itself is not a number. Infinity is a concept. So we actually say that this limit right here is infinity. But what that really means is that the limit does not exist in the positive infinity direction. In other words, it fails to exist going vertically because it is what is called unbounded behavior. Means it keeps on going without bound. So when we say that the limit is infinity, it really is just telling you that the limit fails to exist in the positive infinite direction. It doesn't mean that there is actually a limit. So don't confuse that, because a lot of times we say the limit is infinity, but what it really is just telling you that the limit fails to exist going in the positive direction. In other words, what you actually have there, and you already knew this, we have a vertical asymptote at x equals 0. So if you see a limit of infinity, or likewise you could see a limit of negative infinity, it just means that you have a vertical asymptote there, and the limit fails to exist in either the positive or negative direction. That's what it's trying to tell you. It doesn't mean that there's an actual limit. All right, and then the last one, and this one will come up, and this one is probably the most useful one in the beginning here. What we have is we have the function, the absolute value of x over x. So this one is really important for us to actually be able to graph, because this is going to give us a really good visual here. If I want to approach x equals 0, first of all, I know that if I plug 0 in, I'm going to get a 0 on top, 0 on the bottom. That's a problem. There's going to be some kind of hole there. There's a little bit more to this one. if I were to plug in values to the right of 0, and so any positive values you're going to think of, start with the easy ones. If you plug in 1, you get the absolute value of 1, which is 1, over 1, which is still 1. So I know that over here, if I plug in 1, I'm going to get out a 1. How about if you plug in 2? Well, if I plug in 2, I'm going to get 2 over 2, which also is 1. If I plug in 3, I'm going to get 3 over 3, which is 1. If I plug in 4, I'm going to get 4 over 4, which is 1. So what you should see is anything past 0 in this direction is always going to be 1. It's just a horizontal line going through y equals 1. Make my dots a little bit bigger so I actually hit them. But at 0, I know that I don't have a value, I have a hole. Now what happens when I go to the left of 0? Because there's a possibility of having the graph to the left of 0. Well, now if I plug in -1, well, the numerator, if I plug in -1, becomes positive, but the denominator is still negative. So what I would get is +1 over -1, which is -1. So that's right here. So when x is -1, y is -1. If I go to -2, the absolute value of -2 is 2 over -2 is going to be a -1. So that's going to be -1. Hopefully you can see that no matter where I go to the left, the value will always be -1. And once again, I have a hole at 0, so we'll over-exaggerate that and make this thing go off to the left. Man, I'm really bad at hitting my dots today. So there you go. So that's what the graph looks like. So what is the limit as x approaches 0? Well, if you approach 0 coming from the left-hand side, if we approach 0, the limit of that seems to be approaching -1. But the limit from the right-hand side seems to be approaching a value of +1. So this limit also fails to exist, or does not exist. Does not exist due to what's called differing behavior. Differing behavior. And it's differing behavior from the left and the right. So one limit coming from the left-hand side is one thing, one limit coming from the right-hand side is another thing as you approach the same x value. Therefore, you have differing behavior. The limit cannot exist. The limit must be the same from both sides in order for the limit to exist. And that's going to actually take us to the next part, which has to do with one-sided limits. So I'm actually going to switch things up a little bit here. So I apologize if you're the kind of person that feels like you have to go in order. I'm not going to finish this page just yet. We're actually going to go to the last page, and then we're going to come back and finish the one that we just did. So one-sided limits. I've already kind of mentioned what this is talking about. A one-sided limit means what is the limit as you approach a value from only one side. So we have this notation right here, and you have to be careful to look at it. The first one has a limit as x approaches a, and then it's got like a negative sign after the a. What that indicates is we want to know what the limit as x approaches a is from the left side. The negative side, think about a number line. Negative values are to the left, positive values are to the right. So it's what is happening as x approaches a from the left side of a. So we would say that the limit as x approaches a from the negative side or from the left side of f of x is L. If that's the case, then what we say is the limit of f of x as x approaches a from the left. That's what the little negative means. Likewise, if we have the next one down where you've got the little positive sign afterwards, and make sure that this is afterwards, not beforehand, because negative a is completely different than approaching a from the left, because negative a is a value where approaching a from the left is not. So in this case, it's the limit as x approaches a with a plus sign. That just means the limit of f of x as x approaches a from the right. So again, positive means right, negative means left, and it has to be after the a. That indicates the direction. So the actual definition of a limit. The limit as x approaches a, notice no sides there, of a function equals L if and only if, that IFF is shorthand notation for the words if and only if. That means that there's only one way that this will happen. You have to have these next two things. The limit as x approaches a from the left-hand side of f of x equals L, and the limit as x approaches a from the right-hand side of f of x equals L. Layman's terms, the limit from the left has to equal the limit from the right. They have to have exactly the same limit, have to have the same y value as a limit. If that's the case, then the limit exists. If that's not the case, if the left-sided limit and the right-sided limit are different values, the limit fails to exist, differing behavior. So now let's go back to this page and we're going to finish this up. The definition of a vertical asymptote. Well, first of all, a vertical asymptote is an equation of a line, and it's x equals something, and we're going to say that it's x equals a, is called a vertical asymptote of a curve if at least one of the following is true. And I kind of mentioned this before. If the limit as x approaches a goes to either positive or negative infinity. So what would that look like? We've already done one similar to that. So let's say that we have a graph that looks like this, and we have a vertical asymptote right there. We'll call that A. If the graph goes to positive or negative infinity, so maybe it looks something like this on the left, and then it looks something like this on the right. Both of the graphs at the left and the right of A are going up towards infinity. It could also both be going down, but they both have to go in the same direction. As x approaches A, then you have a vertical asymptote there. Or if just one side of the graph goes towards infinity, or the other side of the graph goes towards infinity. I'm only going to draw one of these, sketch one of these. Again, so maybe A is out here, and you've got your vertical asymptote. So, one side of the graph goes down towards negative infinity. Maybe there's nothing even on the other side of the graph. Maybe that's the whole graph right there. Then you have a vertical asymptote. So the definition of a vertical asymptote is basically that if you have a limit as x approaches that vertical asymptote and it goes to infinity, that's telling you that there is a vertical asymptote there. So again, last time, remember that infinity is not a number. Infinity is a concept. It does not mean that the limit exists if you say that the limit is infinity. It tells you how the limit fails to exist. All right, a lot of concept in these two videos, very important stuff. The ideas from the first video, just graphically looking at a limit, not too difficult. The concepts more in the second video, much more to think about there, so it's very conceptual. So that should be plenty enough for that lesson. Hopefully that's good enough to be able to get your homework done.